We will split this lesson into two parts. The first part is going to focus on understanding vector equation of a line, how to write them, the different forms. And then the next lesson is going to focus on the different skills and the different type of questions that would show up and how would you approach them. So what kind of base knowledge you need to actually solve them. So once we've established everything related to vectors and so on, we now need to be able to not only represent points in vectors, we also want to be able to represent lines using vectors. So this is not very different from you writing a straight line using gradient intercept form or general form and so on, something you've done previously, but now we're expanding it to the world of vectors, and we're going to deal with it in 2D and 3D. So I'm going to start with actually establishing how the equation is formed, so the kind of the proof behind it, and then how do we write the equations and the different forms. So let's say you have this picture, you have a vector A, and it has a position vector lowercase a with components A1 and A2. And I have a vector B that is not linked to A, but this vector B, I'm just representing it with a line here. So let's think of, I want you to think of how many lines can you find that can go through A and is parallel to vector B. So try to think of the answer there, and there's only one unique line. So if I can represent this one unique line, I'm going to draw it there using that dotted line. So that dotted line is parallel to B and it goes through A. So can I actually define this line? I want to be able to define it. Obviously it doesn't only go through A, it goes through other different points, but the basics that I started with here was that it has to go through A and is parallel to B. So how can I actually define this line? Well, I want to define it using any other point. So I want to be able to find any other point with relation to these two facts that I know. This is similar to, for example, when you're trying to find the equation of a line using gradient intercept form, and you have information about the gradient and the intercept. So you have two pieces of information and you're using it to find any value of x and y that lies on the line. So it's the same idea. You have two pieces of information, something that you want to be parallel to, and a point that your line goes through, and using these two you should be able to find any point on the line. So let's start by actually trying to define these any points on the line. So let's say I have a random point r and it has a position vector x and y. So I'm trying to find this value. So how would I go about that? So the position vector of r, if we think about it, is from O to R. Think of you having the origin anywhere, somewhere here, let's say. So you're heading from O to R. So to get from, so the vector r has position vector O to R. And then, well, O to R can be found by taking O to A. And then this is O to A. And then taking A to R. So that's another way of defining O to R. So we're setting it up right now. Well, we know a couple of facts here. We know that O to A is basically just A. So this is basically just a vector A. And I know that AR, by the way I've established the line, is parallel to B. And we know that when two vectors are parallel, I can represent this as a scalar multiple of my parallel vector. So I can rewrite AR as a scalar multiple of vector B because I want them to be parallel. And then by establishing this, you get the actual vector equation of a line. So this is what we're trying to get to here. This is the vector equation of a line, and you can represent it here as like a straight equation or in component form. And that's the proof for the equation. So just to point out, this is x and y. It's a point on the line. Just like when you write an equation of a line, for example, 3x minus 2, you keep the x and the y as they are because you might want to substitute and so on. These represent points on the line. It's the same idea. We keep the x and y here as variables, and then the first vector is a fixed point on the line. It's a point that you know goes on the line, and it's what we started with in the beginning, how we established the vector equation of a line. And then the other vector is the direction vector. So you'll see it throughout the questions. We'll be referring to this is the direction vector. So this tells you the direction that your line is going to, and we use it a lot for different lines. You'll see how we do that. So as usual, the concept can be extended to 3D. You just have x, y, and z, a1, a2, a3, and so on. Now, what if I don't have a point and a parallel line? What if I want a line that goes through two fixed points? Again, something typical that you might have seen when dealing with straight lines. I could give you a gradient and a point, or I could give you 2 points and I'll tell you find the equation of a line that goes through 2 points. Same idea with vectors. I'll give you 2 points and I want a line that goes through them. So you have we can still create the same thing. What we're only missing is the direction vector. So it's fairly simple. We have the same structure. You have the point on the line, and the x and y, so as a variable, and then in here you have a known point. Well, you can pick any, either a or b. The position vectors of a and b, it does not matter. You can pick either. And then plus a scalar multiple, you now need a direction vector. Well, the direction vector is going to be, if you have points a and b, and you need something that's parallel to it, so obviously you need to find a, b. You can also try and find b, a. It does not matter. It will still give you the same answer with slightly different signs, but it will give you the equation of the same line. So you want to find the direction vector AB. First, you put it here, and then you have one of the points here. And same thing, you can extend this concept to 3D. So once you've established the equation of a line, using vector form, so this would be a vector form. This is an example. You have this point exists on the line, so this is like our point A, and this is the vector that it's parallel to, and we're taking a scalar multiple of that. So this represents a point on the line. If I need an x, y, and z, all I have to do is replace lambda with an actual number, and solving this or simplifying it will give me a point on the line. So very similar to doing y equals to mx plus c, for example. You replace the x with a value, it gives you a y value, and therefore you get a coordinate on the line. Same idea. Now, we don't only have one form of writing an equation of a line. This is called the vector form. We also have something called the parametric form and something called the Cartesian form. So you need to be familiar with all three and know how to move from one form to another. You need to be careful when questions ask you to write in a specific form. So if I want to change to parametric form, what you're actually doing, if you notice the highlights here, you're actually just taking each row at a time, but making sure that you take the scalar here. So parametric form is you writing three different equations, one with respect to x, one with respect to y, and one with respect to z, and they're all in terms of lambda. And when you're in 2D, so imagine you're hiding the z part. When you're in 2D, you can use simultaneous methods. You eliminate the parameter, and then you end up getting the equation in gradient intercept form. So again, very close to home, something that you've done before. So this is writing it in parametric form. And then writing it in Cartesian form is basically just taking the parametric form and making lambda the subject. Once lambda is the subject, then all the three equations are equal to each other because they're all equal to lambda. Again, in 2D, I can imagine you're hiding the third component, and you can rearrange it and write it. You're able to write this in general form or gradient intercept form. Again, something you've seen before. You can move from vector form to Cartesian form. If you notice here, the values in the direction vector are actually the denominators here, and the points are the numerator, but with the opposite sign. So just in case you need like a quick jump from one form to another. And then obviously you can also skip from this form to here and so on. So let's do one quick worked example just to make sure that the concept is solid here. So I have a point A and the given point, and B is the direction vector. So I want my line to be parallel to this. So if I want the vector equation of the line, all I have to do, you can write it in different formats. I could write this as R equals to 1, 2. That's the point I wanted to go through, plus a lambda 3, 4, and that's it. So lambda is real number, so quite straightforward. You can also, instead of writing R, you can say, well, it's xy 1, 2 plus lambda 3, 4. So that's the vector equation of the line. Now, once you have the vector equation of the line, you can then convert it to Cartesian form. You can convert it to parametric and then Cartesian, or see the trick that I showed by taking this as the denominator and the opposite sign here. But let me just take the long route for now. Writing it in parametric form, this will be x equal to 1 plus 3 lambda. Don't forget the scalar. And 2 plus 4 lambda. And then if I want to make lambda the subject, it's going to be x minus 1 over 3. And this is going to be y minus 2 over 4. And then writing it completely in Cartesian form, we have this. Okay, so again, we could have taken the 3 and the 4 in denominator and the opposite signs here. And then I need to write it in gradient intercept form. So this is what I've mentioned. When you're in 2D, you can easily change it to gradient intercept form. Well, let's try and do that. What I could do is just cross multiply to get rid of the denominator. So we get 4x minus 4. Obviously, in gradient intercept form, you want y to be the subject. That's what I'm trying to do. Minus 6. And then I'll take 6. I'll simplify this. And then I'll divide by 3. I'll just keep the y here. 4 over 3x plus 2 over 3. So this is an equation, the gradient intercept equation of this line. But we started with vector form, and notice how we changed to a form we're familiar with. Another example again, just to reinforce. So I want a line that passes through 2 points now. So as mentioned, I want, you have a point. You can pick any of these points to be the, remember when we said this is the format? Well, we're in 3D now. So you can pick any of these to be your point on the line. But then this has to be a direction vector. So you need to find the direction first. So let's try and find AB, or you could do BA, that's fine. AB is going to be vector B minus vector A. So it's going to be minus 3, 1, minus 2, minus 1, 0, and minus 4. And that's going to give me minus 4, 1, and 2. So that's my direction vector. So now if I want to write the vector equation of the line, I know it's going to be any of these A or B. I'm just going to pick A plus lambda of the direction vector, which I know is this. So this is what I wanted it to be parallel to. Now, part B, I want to write in Cartesian form. I'll use the quick shortcut, which is keeping the denominators as these points. You can skip writing the 1 here, it's fine. And then we have the opposite signs, z plus 4. And that will be the Cartesian form of the line. So just a note on the different forms of the line, because you might start some questions differently, you might have different points and so on. So let's say this question that we had just a few slides ago. If I have this direction vector, and if I, as I said, to find other points on the line, this is the one given, I can substitute any lambda, and different lambdas will give me different points on the line. So this is nice. But then I could also look at the direction vector, and I can take any multiple of the direction vector. If you notice, this is a times 2, times 3, and so on. So these are all direction vectors. Now, if I want to write the vector equation of a line, well, it started with this 1, 2, and 3, 4. But you can actually pick any point on the line, so any of these, and any of the direction vectors. So notice, and it doesn't have to be corresponding. So notice how I picked 7, 10 in here, and then I picked the 6 to 8. And this describes the same line as the beginning. So it's just to make a point that vector equations can be written differently. You don't have to stick to the exact direction vector, but sometimes when we see that, for example, 6, 8 is a multiple already of a much smaller vector, we tend to take the smaller vector, because the smaller it is, the much easier the calculation is going to be. And then the points as well, you can pick any points. That goes back to, what if you're given 2 points? Does it matter which one you pick? No, it doesn't. And finally, what if you are given a, you want to write the equation of the line, but you need to use something called the normal. So the normal is another way of saying perpendicular or orthogonal. So a normal vector is 90 degrees to your other vector. And we will use this wording very frequently. So the normal vector is always perpendicular to your line or your point. So if I have instead of having a direction vector, I have a normal vector. Well, how would I actually write the equation of the line? So I know this is the equation that I want to write, but all I have is a to p, and then I know the normal vector. So I know what the normal vector is in this case. So what do I do? Well, let's actually just write out what we know. We know that if two things are perpendicular, their scalar product is 0. So if I take the vector n and the vector ap, I know that their scalar product is going to be 0. Well, ap is just basically vector p minus vector a. And we know from the scalar properties, I can expand this or distribute this, and I get np minus na. So scalar products here, and they're equal to 0, so I can move na to the other side, and I get this. This is the other version of a vector equation of a line, but this time using the normal. This will be the normal, so this will be given in the question. So this is given. This is your point, you don't know what it is, xy, and this will be a given point. Okay, so this is the a that we start with, for example. So just to keep that, just like the direction vector, the normal vector is not unique, so keep that in mind. Now, most of the time they'll give you the normal vector. In the case that they don't, and usually it's the case in 2D, if they are giving you the direction vector instead, and they want you to write it in the normal form, then a possible normal vector will be you first of all swapping these two around, so d2 and d1, and then d1 you negate it. So by doing that, this is normal to this, and you can check if you have d1, d2, take the scalar product because d1, d2 has to be here. This is d1, d2. And you have the normal to it. So this will be d1, d2 plus d2 times negative d1, which will give you 0. So if you are given a direction vector and you need the normal vector, you can do this. Otherwise, in 3D or in some other questions, they actually tell you what the normal vector is. So this is how you do the vector equation of a line. Another video will go through several skills, about 6 or 7 skills that you'll need to be able to solve different type of questions for vector equation of a line.